Then let's return back to the idea of decomposing the matrix A times A equals lower matrix times upper matrix, where lower matrix is the form like this, 1, 1, 1, 1 in the main diagonal, and then upper diagonal 0, 0, 0, 0, 0, and the lower diagonal may have some numbers, and multiply by upper diagonal matrix that we can obtain from Gaussian elimination, and then 0 elsewhere. But this is the form that we could obtain, and I showed you the idea of getting these things. And if you have a question about these things, ask me. If you don't, then I will return back to the reason why we are getting these things briefly, and then go to the next idea. The reason that we get this thing, the reason why we get this thing is here. If you look at this, then A new matrix is obtained by A old matrix minus this one. And if we move this to the left-hand side, it's nothing but the matrix multiplication. In other words, matrix multiplication with this lower triangular matrix multiplied by this one. So essentially, what it does here is doing this thing, right? Doing this thing, decomposing A matrix into L and U. But theoretically, you don't have to completely understand the step. But practically, you should know what happens here and how to obtain these things. But can we then mix these things into one matrix? Initially, we had A matrix, right? Initially, we had A matrix. Then can we hold both L and U in this A matrix? And the answer is yes. Take a look. After doing the Gaussian elimination, this portion is nothing but U, right? This portion is nothing but U. Now, these are supposed to be 0. But instead of filling this with 0, we just attach multipliers here, right? We just insert multipliers here. Then just A matrix now became L and U matrix. Later, you can recoup these things by just copying these things or doing something. So essentially, we can do the matrix multiplication, L and U, from the given matrix, A. So matrix decomposition is done. But practically, what happened is this one. A matrix converted to strange matrix containing both L and U. Then what things should be attached in my program? Did I kill everything? Then let's attach just one line to hold these things. So what should be attached here? Only one thing is enough. What is it? This is it. In other words, AIK, right? AIK. Yeah, this should be correct, right? This should be correct. In other words, AIK was not even touched. So AIK now keeps M. This is it. By this way, we can create the format. So let's practice this thing one more time. Then check what kind of decomposition happens. So take a look. Initially, this is the matrix, right? Initially, this is the matrix. Then what I will do is the decomposition like this. But making it bigger is not very nice, so I will make this smaller and then later return back. So it's not Gaussian elimination anymore. So file save as G2, right? I will save this in the second position. Then the number of unknowns is 3 and the x is. Do you follow me? So I'm now decomposing the given matrix using this, and this Gaussian elimination part isn't even necessary. So this is the LU decomposition program, believe it or not. So let's do it. Let's run it. Oh, I see. Yeah, we don't have the last column, right? We don't go through the last column. Done, right? Done. Then can you interpret this thing? A now became this one. Then can you interpret this result? What does this mean? It means what? L matrix is what? These things with 1, 1, 1, 0, 0. U matrix what? This thing. So to verify, instead of writing down these results somewhere else, I will just multiply 1, 0, 0, 4, 1, 0, and then 1, negative 1/3, 0, or 1. So I create the upper triangular, lower triangular matrix by following the guideline, right? Upper triangular entries are 0. Main diagonals are 1, 1, 1. And then lower diagonal matrices are determined by these numbers, right? 4 is here. 1 is here. Negative 1/3 is here. Multiply by upper triangular matrix is what? 1, 2, 3. 0, minus 3, minus 6. And then 0, 0, 4. Then we should get the original matrix, right? We should get this matrix. So let's do it. Did we get it? So I completely showed you the LU decomposition from Gaussian elimination. So essentially, we don't have to do very much. We just tweak a little bit. Just do bookkeeping to remove like unnecessary column entry and store the M that we recycled in each step, right? We recycle M. M is calculated and M is stored in empty spot, right? In correct empty spot. So only one line is added to create LU decomposition. And back substitution is not even mentioned. So I completely explained two different methods, but essentially they are the same. Gaussian elimination and LU decomposition. And if you have a question, ask me. If you don't, then I will mention about the reason why we are doing LU decomposition style thing. Questions? Then, this is the reason. Assume that we have a general matrix A, x times b. Then, to find x, we need to do some hard calculations such as finding inverse and n. This is very difficult, right? Generally very difficult. But now we have LU decomposition. LU x equals b, right? We decompose A into L times U. Then what happens? First of all, we don't regard this as the given problem, but we regard this problem as A times something equals B with special L. This problem is a special problem with L, not general A. Then what is the pattern? This L looks like this. In the previous case, L is this one. In the previous case, L is 1, 4, 1. Right, this is right, Z matrix, right? B. Anything can come on the right hand side, right? Any set of numbers can come on the right hand side. Do you follow me? So we don't regard the problem as AX equals B, but we regard the problem as L times something equals something on the right-hand side. So say E happen to be, what numbers do you like? You may pick. Right? So we have this kind of problem. Then, can you solve for Z1 or not? Can you solve this for C1 or not? Z1 is very easy to determine. Why? Z1 times 1, 0, 0 equals, right? Z1 times 1 plus 0, 0 equals 5, right? So Z1 is what? 5. Because Z1 is 5, you can use 5 here, right? Then 5 times 4 is 20. 20 plus Z2 equals 6. Can you calculate Z2? So with this, Z1 equals 5. And then with 5 here, 20 plus Z2 equals 6, or Z2 equals this, and then it is negative 14, right? With 5 and negative 14, then this is multiplied here, right? This is multiplied here to get the result. Then 5 times 1 is 5. Negative 14 times this is 14 third plus Z3 equals 7. So Z3 is what? 8 thirds, right? Z3 is 8 thirds from this calculation. So negative 8 thirds. Right? So we could calculate Z1, G3, G2, G3. Very easy. It's not really solving. It is forward substitution. Do you follow me? We find Z1, and then we substitute right forward, right? And then we calculate G2, and then we substitute Z1 and G2 forward substitute, and get G3. So it is forward substitution.
So when we're just substituting Z for UX, are you going to go back and find X from Z?
Right. Yeah. And then after finding Z, it's not our goal. Our goal is finding X, right? So we find this relation. So after this, UX equals, we have the relation UX equals Z, and then Z happened to be 5, negative 14, and then negative 8 thirds, right? It is found here, right? Then take a look. U is the upper triangular matrix. U is the upper triangular matrix that we calculated. That is, in this case, 1 to 3. And then finally, this number is 4. Right? This times x1, x2, x3 equals 5, negative 14, negative 8 thirds. Can you find x3? This is nothing but back substitution. We determine x3 by solving this line, right? You can directly find this one. Then x3 is equals what? Negative 2 thirds, right? And then x3 is here. Then this times x2, and then negative 6 times the number that we found equals negative 14, and then we can determine x3. Straightforward back substitution. In other words, once you have LU decomposition, you don't really have to find the inverse. You don't really solve the problem from scratch. You solve one forward substitution and one back substitution to determine x, y, z. In other words, it is extremely efficient. Assume that you have 10,000 unknowns. Finding the inverse of 10,000 by 10,000 matrix is very costly, difficult. But once you have LU decomposition or some kind of decomposition of this sort, then you can do the one forward substitution and one back substitution to get the solution. Then essentially 1,000 time calculation with appropriate sums, and then 1,000 back substitution with appropriate sums, then done. Instead of finding complex inverse. So this is the reason why we are doing LU decomposition or some sort like this. This isn't the only way, but it's very efficient way. In other words, from this point on, people's goal is the determination of this kind of thing, right? 0 means zero entries. So from this point on, we will focus on this kind of direction. Why? Because the advantage is huge. With this one, you can determine the solution, not by solving it, but by just substituting the result. Substitution means back substitution size. In actual programming, as you saw, this kind of thing is back substitution, right? So almost the same thing is forward substitution. So by just doing this kind of thing, we can do the calculation. And it's very fast and efficient. Then, what kind of things were considered? One thing is LU. The other is QR decomposition. And later we will see L transpose. So there are many things people developed. Even different LU, different LU decomposition exists. Upper, lower, triangular, but different. In other words, decomposition is not unique. You can decompose A matrix into this pattern by using different methods. Oh, sorry. QR is different story. I was confused. Right. QR is a different story, but LU or L transpose and different L different. QR is just a decomposition, but not lower or upper triangle. So this kind of direction will be studied very soon. And if you have a question, ask me. If you don't, then we'll continue. Then the next thing is this thing. Cholesky focused on this direction and thought, oh, there is no reason to use L and U. What about L and L transpose? Because L is lower triangular, transpose of the matrix L should be upper triangular. In other words, by using just one matrix, we can achieve the goal. So it's called Cholesky method. So we can find, in this case, just finding one matrix is enough because the other is the transpose. So this direction is developed. And later, people modified this thing by adding diagonal matrix in between, right? L transpose is used, but somewhere in between, diagonal matrix is attached. But this is beyond this level. So I don't cover this thing. But if you are interested, you can study this. So pure L transpose decomposition is unique. Why? What else can satisfy this kind of relation? It's impossible, right? Only one matrix satisfies this thing, in general A matrix. So let's find this kind of L matrix. And instead of writing down the formula on my own, I will give you the summary. I will magnify it. Take a look. So assume that A matrix is very nice. Just instead of worrying about definition, A matrix nice enough. Right? A matrix not very general, but nice enough. Then we can do this thing. It is here, but it's a little complete. Let's not worry about bad situation. In other words, LU decomposition worked very well for general matrix A, but this Cholesky method applies to the smaller number of matrices, right? Then you can do this thing. And how can you get this thing? First of all, we get Lij using this thing, but it is initially empty. It's empty loop because take a look. I is 1, 1 minus 1, 1 to 0 is impossible. So empty loop. Initially we determine L11. Do you follow me? Initially we determine L11. And then now we go back and then loop, then it is 1 to 1. It is only one term. Then we can calculate this kind of thing. And then we calculate this thing. And then we calculate this thing, and this thing, and so on. And we can calculate these things by just using this loop. You can implement these loops straightforward. Then we can calculate all the L values. how can you get this kind of formula? That is the major concern in theory. I will briefly show you how to calculate, how to find these kind of things theoretically. But programming-wise, how many lines? Essentially, whole line with ends, right? Ends. Whole line. So let's do it. It's very straightforward calculation. Nothing more than matrix multiplication. So it is symmetric. So like A11, A12, then A12 should follow because it's symmetric. And A22, and so, right? This kind of symmetric matrix then equals L11, L21, L31, and so on, L22, L32, and so on, right? And then 0, 0, 0, 0, 0. And then 0, 0, 0, 0, and so on. And then L11, L21, L31, and so on, L22, and so on. So we can multiply these things. Then, what is the first entry of the multiplication? L11 squared. Straightforward matrix multiplication. Can you calculate the L11 then? What is the relation between this one and this one? L11 squared is A11. Then we can get L11 equal to square root of A11. Done. So you can do these things all the way down, right? Theoretical, if you are interested. And you will get exactly the same formula as the one described. So essentially, it's straightforward multiplication. And then after solving this for L11, L12, L21, and so on, we get the result like this. We get the result like this. So essentially, it's very straightforward case. Any questions? Then the next case is more restricted. Generally, we can use very fast algorithm. We can use a very fast algorithm when you have this kind of case. So this is called what? Do you know the name of this kind of matrix? Tri-diagonal matrix. Tri-diagonal matrix, right? Tri-diagonal. So this diagonal has non-zero entry, and then this upper diagonal has non-zero entry. This lower diagonal has non-zero entry. So other than these, all zeros, right? So tri-diagonal tri-diagonal matrix is given. Assume that tri-diagonal matrix is given. Then we can determine the decomposition very fast, extremely fast. And when do you see this kind of thing? When you see finite element or finite difference method, in some cases you can see this kind of. Then what is the formula? So let's rewrite it. So I will show you the case. So take a look. I used A letter to represent the main diagonal, right? A letter is used to represent the main diagonal. And then C is used to represent upper diagonal. And then B is used to represent lower diagonal. And all others are zeros. Do you follow me? So A, C, and then B. A is upper diagonal. A is the main diagonal, upper diagonal, lower diagonal. Then what happens? We can decompose the matrix A into L and U, but instead of using L and U, L is replaced by M and U is replaced by N, right? So M and N matrix. Of course, you could use L and U, right? So M and U decomposition. Essentially, how can you get these things are described here. Very, very simple loop will do it. Very, very simple loop will do it. By just running appropriate loop like this, you can do the calculation. And as you can see, one thing is mandatory. Take a look, because it's lower diagonal, including main diagonal, it requires two diagonal forms, right? Two diagonal entries. And this requires also two diagonal entries, but one is mandatory, right? Main diagonal is 1. That means only gamma is required. So we can determine all these things. But as you can see, what is B? In the first place, B is what? Here. So in this sense, only thing that we need to determine is this alpha 1 diagonal and the gamma diagonal, gamma upper diagonal. These are the only two things required. So this is called the tridiagonal decomposition. You follow me? At least the lower diagonal of the original matrix is recycled in M. And then 1, 1, 1, 1 is right filling M, right, main diagonal of M. Yes. Right, yeah. Right. Upper and lower of not but different. Alpha is not A. Right. But some part is the same, right? Some part. B is the same. Here 1 somehow occupies. So we determine only gamma and alpha, then we can determine upper and lower. Of course, all these things can follow from straightforward calculation. The same calculation as the one. So if you doubt it, you multiply this by this matrix, right? Then you can determine these kind of things, right? And then multiply these things, and then match, and then do the calculation to get this kind of formula or relation. In any case, when you have tridiagonal matrix, we can easily decompose, and it's extremely fast. This is extremely fast, and as you can see, the speed is amazing. Assume that you have n unknowns, then some number times n will do it. Some number times n will do it. Assume that you have 10,000 unknowns, then maybe 40,000 or 50,000 may do it. But in other methods, sometimes n squared or n cubed calculation is required, meaning n cubed case means 10,000 multiplied by 10,000 multiplied by 10,000 multiplied by some constant calculation may be necessary. But here, it is just 10,000 times a few, like a certain number we'll calculate. So essentially, we considered all possible cases for nice matrix. These do not happen for general case. General case is handled by LU decomposition. But assume that we have nice matrix, then we can use Cholesky L transpose O, or when you have tridiagonal one, then you can use this method. Any questions? Then the next idea is completely new. This kind of direction is called exact direction. Exact calculation has limitation and difficulties when the size of the matrix grows. When the size of the matrix grows, it's very tough to do exact calculation. Assume that you have 100,000 by 100,000 matrix. Then doing exact calculation is almost impossible, because when you use LU decomposition, small error will like propagate and accumulate and cause big trouble later. And the result will be unreliable. And in fact, many problems have more than 100,000 variables. or unknowns. Then how can you handle it? So that's the next consideration. Because of this thing, whole new different idea was considered. And the idea is this. Assume that we are solving this 5x1 plus 2x2 equals 7 and 3x1 plus 4x2 equals 7. So assume that you are solving these solving this system. Then the whole new idea is this. Instead of finding the exact solution, we develop some strange relation like this. Not very strange, but some relation like this. Oh, what about solving this for x1? If you solve this for x1, what happens? x1 equals what? 7 minus 2x2 over 5. Do you follow me? I solved this for x1. What about solving this for x2? x2 equals what? 7 minus 3x1 over 4. And in fact, this method is used. Believe it or not, when you watch TV, this thing is behind the technique. Then let's do it. We want to solve it. So, but then what is the process? The process is this. We initially guess x1 and x2, right? So x1, x2 happen to be our guess. Oh, let's say about like 0.7 and 0.8. So I guess the solution. Because of our guess, what happens? Because of our guess, this guess goes into it to calculate x1. Do you follow me? Then what is the next result? If we follow this case, what is the next result? 0.8 is used here. 0.8 multiplied by 1.6 is used here. Then 5.4, right? 5.4 over 5. Do you follow me? Because of this, I could calculate it. Please calculate x2. x1 is 0.8. Right? We can get this thing. So instead of me doing these things, I will let MATLAB do these things. But understanding the idea is very important. Do you completely understand the idea? From the equation, we generate some related equation, right? From this equation, we find this related equation. From this equation, we find this related equation. Then using this related equation, we iterate. In other words, from this, we get this. From this, we get the next one. From this, we get the next one. So we generate these things and hope for a convergence, right? It may converge, right? If we do these things, it may converge. So this is the whole new idea developed. And this is, in fact, used in real-world situations. But understanding the idea is very important. And if you don't understand the idea, ask the idea part. Do you follow me? So we generate this kind of relation from the given equation. And then we initially guess. And using the guess and the relation, we plug in, right? x2 value is plugged in to determine new x1. x1 value is plugged in here to determine x2. Now, these values are plugged in twice, right? So this value is plugged in to determine new x1, right? This value is plugged in here to determine x2, and so on. So we continue and continue. So let's really see the progress. Seven minus 2x2 over 5 and 7 minus 3x1 over 4. And initially we used x1, x2 equals 0.7, 0.8, maybe. I just wrote down this verbatim, right? Initially x1, x2 are determined, and then x1, x2 are used here to determine new x1, x2. So let's run it. How can you do it? The only way is using x, right, instead of this. Let's use x. And then, instead of saying this, do x equals x2 and x1. Will this work? I hope. So we calculate this stuff. Do you follow me? So from x1, x2 pair, we get new x1, x2 pair, right? So from this x1, x2 pair, we get new x1, x2 pair. And then now, from this x1, x2 pair, we get new x1, x2 pair. From this pair, we get new one, we get new one, we get new one, we get new one. And take a look. Does it converge? It may or may not. So let's try. So it converges, right? So this is the idea behind the whole new approach. So please browse this thing and ask questions. So essentially what you do is this thing. We are solving the equation not by straightforward exact idea, right? Instead of exact calculation, new idea is creating this kind of relation and then do the iteration, right? So we do the iteration until it approaches 0. It converges, right? Then let's make up one more case. Oh, what about 3 by 3 case? So I will pick some other case. So 9x1 plus 3x2 plus 4x3 equals 16, right? And x1 plus 10x2 plus 5x3 equals 16, right? And then 2x1 plus 5x2 plus 7x3 equals 14, right? So we want to solve this case. Then let's do it. So what kind of relation can you get from the first equation? x1 equals what? x1 equals what? 16 minus 3x2 minus 4x3. What about x2? Can you get x2 from this relation? What is it? 16 minus x1 minus 5x3. What about this one? x3 is equal to what? 14 minus 2x1 minus 5x2 over 7. Right? And then we can we can guess the solution. Oh, let's say x1, x2, x3 triples are like 0.2, 0.5, 0.7. So we initially guess and then use this relation to create new set of points. Then let's do it. 16, negative 3, negative 4. So this is the initial guess, right? This is the initial guess, 0.2, 0.5, 0.7. Now, x1, x2, x3, triple will be determined. Then it is 16 minus can someone let me know the equation? 3x2 for x3 over 9. The next one, 16 minus x1 minus 5 times x3 over 10. Finally, 14 minus 2 times x1, 5 times x2, 27, right? So this is just verbatim implementation. So from 0.2, 0.5, 0.7, right? 0.2, 0.5, 0.7, I got these numbers, right? Now, these are plugged into this thing to get new x, right? New x1, x2. And then now plugged in to this thing, plugged into this thing. And what I do is just looping it, right? Because I didn't program it, I should do this, write these things over and over again. But if I programmed it, it might run automatically, right? So once you do these things, it may converge, right? So essentially, even programming is not very difficult, right? Programming of these things is not very difficult. Then let's now return back to the theory part. So as you can see, we now have whole new idea developed by Gauss-Jacobi, right? And from this one, we somehow extract one unknown, right? Usually diagonal unknown, right? So initially we had sum of many terms, but we extract just one, and then the remainder moves to the other side. Then we can solve this for xi, right? So we can solve this for xi to get this kind of equality, right? So this is called Gauss-Jacobi method. So let's return back to my note. Take a look. Initially we had the equation, right? So from this equation, we extract x1, right? 9 times x1, and then we describe x1 in terms of the other, right? x1 is described by the other. And then here I extract x2, and x2 is described by the other. And x3 is also described by the other. Then what about the possible improvements? There are two possible improvements considered in a basic level, and later people developed more. Here, this is the situation. Initially, we have found or guessed x1, x2, right? And then x2 determines next x1, x1 determines next x2, right? Up to this point, look fine, but even this step we can improve. How? Take a look. Once we have determined x1 by doing this, right? Once we have determined x1 by doing this, why should we use previous x1? Why do we have new x1? Do you follow me? Instead of crossing these things, what about just recycling this thing? This is the difference. The crossing is Gauss-Jacobi, but recycling, in other words, x2 determines x1. In the determination of x2, we need x1, but instead of getting it from this point, we already have this one. We use this one, Gauss-Seidel. This is Gauss-Seidel, right? So here you can see Gauss-Seidel. So instead of using the old one, whenever new number is there, then use new number. And in fact, what is easier to program in real situation? Gauss-Seidel is easier to program. Why? If you use Gauss-Jacobi, until the determination of the next whole column is done, we should keep these entries, right? We should keep the values in this column until second column is completely determined, because something should be used. But if you use Gauss-Seidel, we can use one memory space. Just x1, x3 are there. And once new value is found, new value replaces the old value. Each time, each position has new entry. In other words, we don't have to have two different memory space. Do you follow me? If you use Gauss-Seidel, we should keep this position until we have determined this thing, right? So we should keep this thing until this is done. And then we can release. But Gauss-Seidel do not need two memories. We can have just one memory space. And once x1 is recalculated, we don't have to have two different columns. Just new x1 overrides. Once we determine new x2 overrides it, right? And so on. And then we return back and we override. So what is easier to program? This is way easier to program. In my opinion, by mistake, he might develop this, just a joke, right? But this thing is possible. So Gauss-Jacobi requires to keep the first column until the end of the second column calculation. Gauss-Seidel do not even care. Just one space is used, and whenever new value happens, is calculated, then just we override the previous value. Always new value is kept here. So this is the idea behind Gauss-Seidel. Then, people did all the easy things, right? These are all easy. How can you improve more? And people really overstretched, right? How? Over. So the next idea is, take a look. We are solving this thing. Assume that we are solving this thing. Then we have this relation. Right? We have this relation. So this is the same thing is used for both Gauss-Jacobi and Gauss-Seidel. Then somebody tried to tweak these things by doing something like this. Oh, what if we... Thank you. So we are tweaking this a little bit. How? x1 is 1 plus, I will use minus first. Doesn't matter, but I will use minus first. 1 minus, what letter do you want? Any letter I will use. Q plus Q. x1. So I will call this right hand side, right? Right hand side. You follow me? x1 equals the right hand side, but now x1 is replaced by this. then I will break this up. Is it very difficult or not? Why did people develop this thing? My simple idea, they should somehow survive by writing papers. So with the form that is already developed, it's not possible to publish. They should somehow change and change. So change. Then, can you solve for x1? Can you solve this for x1? What is x1? Oh, sorry. Yeah, this is correct. This. So we are ready to simplify it, but I don't like reciprocals. So you chose Q, but I will call 1 over Q W, right? So I just changed the letter. Then x1 equals what? x1 equals W times right-hand side, and then minus W minus 1, but you can eliminate minus by using plus and minus, right? Plus and minus, or we can even write in reverse way. I'm not doing very special thing, I'm just rewriting it. Done, right? So you can do the same thing to the other equations following the similar idea, right? Instead of x1, you can use x2, right-hand side, something, right? So you can do the same thing to this case. So please write down the actual formula for x1 and x2 in this pattern. Then what do you get? In this pattern, if we write it, then it equals W times right-hand side, 6 minus x2 over 5 plus 1 minus W x1, right? And here, the same thing, x2 equals W times 9 minus 2x1 over 7 and 1 minus W x2. And we can completely generalize these things, and I will return back to general formula once you completely understand this idea. So you need to write a paper, then change something, right? Change something. Then let's go to the general case. So what if we have general equation like this? How can you take it? The same idea. The same idea. And take a look. We have W thing, right? W thing here. And then 1 minus W thing here. And xi instead of 1, right? And as you can see, this has a special name. This kind of thing is called SOR. SOR. Successive over relaxation. Have you heard about SOR? In my opinion, sometimes SOR is the name, sometimes the full name, sometimes just people call relaxation. So this method is called SOR, and SOR is used to solve actual linear systems. Only one catch is this one. W should be between 1 and 2. If W is exactly 1, then W equals 1 means 1, 0. Then exactly Gauss-Seidel, right? Exactly Gauss-Seidel or Gauss-Jacob. So it should be different from 1. If it is smaller than 1, it's called under relaxation. If it's greater than 1 and then less than 2, it is called over-relaxation. And this over-relaxation is used. So SOR means this one. Then let's run the same thing with SOR. So I will change this thing to SOR. How? W. So W is between 1 and 2. So I will pick 1.2, right? I will pick 1.2. And then now I will attach W here. So let's do it. W times this one plus 1 minus W times x1. Do you follow me? How can I make SOR? Simple. Multiply W and then, excuse me? Oh, I see. Thank you. And then plus 1 minus W times x2. And finally, W multiplied here. And then x3. So I made the SOR from outsider, right? From outsider, I made SOR. In fact, mine is not exactly SOR, but it's similar, right? At least this is the approach, right? Because you should not change x1, x2, x3 simultaneously. Do you know what I mean? You should change x1 and then x2 and then x3. That doesn't matter. So these kind of things are going on, right? So in any case, I can convert the problem into SOR by doing this. So let's summarize what you have studied today. First thing is solving an equation by doing Gaussian elimination by following this loop and back substitution. And then by recycling this, we can get lower triangle of this sort with diagonal equal to 1, 1, 1. And then upper triangular after finishing this step. Finishing these steps, right? And then get this lower and upper. And if we multiply lower and upper, we will get A given by the problem, right? So A can be decomposed into L and U. And why do we care this kind of thing? Because once we have lower and upper, then we can solve the problem very differently. How? First of all, we call this part some vector Z, and then we solve LZ equals B, and then we get Z value. Not by solving it, but by doing forward substitution, right? So by doing forward substitution, we get Z. After getting Z, we solve this thing by doing back substitution. So by doing forward substitution and back substitution, we can get the result when you have LU decomposition. And then, what about different types of LU decomposition? The answer is yes. For nice examples, for nice matrices, it's possible. For instance, how nice? This kind of nice, right? This kind of nice with symmetry. Then we can do LU decomposition or L transpose decomposition, called Cholesky method. Or when you have tridiagonal matrix, such as this one, we can calculate the upper and lower triangular matrix straightforward to get this kind of result. And the algorithm is very straightforward. After this, how can you find the solution? By just doing this, we can determine the solution. First of all, we determine Z. And then we determine X like this. In the past, we did it, right? We determine Z first, right? We determine Z first, and then using Z, we can calculate. Using Z, we can calculate X. So we do the same thing here. So we calculate Z here by solving lower triangular matrix times something equals the right-hand side. And then after getting Z, we use Z to determine X. Then it's very fast. And then now iteration comes. Iteration is breaking up one part from this, right? Breaking up one part from this, and then solve the whole equation for this broken part. Right? Break up some parts from the whole line and then solve this for a broken part to get this kind of relation. And then we do the iteration. But there are two different ways of doing iteration. One way is simultaneous displacement. Right? We have x1, x2, x3, and we keep these things until the next column has been found. And so on. But if we just keep one memory space and then do this thing, it's called successive display. Whenever new xi is found, just use new xi instead of old xi. Then the next idea is relaxing. By just simple trick, we can rewrite the equality this way. I used q initially and then used 1 over q to represent w, right? And then we do this. Then is there any way to determine w automatically? Sometimes, not always, but sometimes. For a nice Poisson equation, it's a differential equation. We have this kind of method. Assume that we have node number n, then we can break up this. And then, how can we really program? Usually, we can add 1 through n or something, but if 1 is missing, how can you do it? Simple. You add all, and then later subtract the specific parts, right? Then we can do it. But it's not required. Some, for instance, MATLAB may not have some function, but some other languages or tools have some function. Then use the sum, calculate everything, and then extract specific to achieve the goal. But this is not required. And the next thing is this. Assume that you use this kind of method, then you see this kind of factor dividing this. Then when does it converge? As you can see, if this denominator is big, then the number here will not be very big, right? So this is called diagonally dominant, right? When the matrix has diagonally dominant case, then the method converges. Then I guess after introducing the idea, I will cover these two cases next time, but I will introduce the idea anyway. But before covering the idea part, if you still have a question about these methods that we learned today, ask it. The next idea is this. Assume that you are climbing the mountain and you want to climb fast. You have infinite enough energy to climb no matter what. Then each time you want to find the steepest road, right? Steepest path, right? Each time you find the steepest path to go up to the top area very fast. And this kind of approach is developed in this solving method, right? So the idea is this. Always find the steepest direction to go to the top. And usually, how can you get the steepest direction? If we follow the direction parallel to the gradient, our vector is parallel to the gradient vector, then you can get the steepest direction. It's from calculus 3. So the next idea is using this kind of thing each time. In other words, initially we started with x1, x2, x3, and so on, xn. So we start off with some point. And then next time, when you determine the next set of numbers, we follow this kind of thing to create a new set of values. Of course, once these things are described, you will see the complexity because these things are behind. And then do this thing, and after finite steps, we will arrive at the top. So this is the idea behind the method. Then what else is possible? I'm overdoing instead of really covering. what else is possible? Up to this point, we were handling linear cases, right? We were handling linear cases. But what if the problem is not linear? In other words, x1 squared plus x2 equals 5. x1 plus 5, x2 equals 3. 2 squared is 3. What? Instead of 2, I will use different number. Cubed is 3. Then, because of these terms, the system is not linear anymore. It's a non-linear system. Then how can you handle non-linear systems is the next concern. So next time, we'll consider two cases. One case is following the efficient way to determine the solution called conjugate gradient method. And the other is handling this kind of system. And here, we use Newton's method. We use Newton's method to get the result. Roughly, almost the same as one-dimensional Newton's method, but we need some kind of bookkeeping to make the same method work. So we will study this next time. And I will be here, and you may ask questions for about 10 minutes, and I will answer the question. And if you don't have a question, you may leave them.